that way people who cannot attend, they still have the benefit of this. Let me just move my keyboard out of the way there. Okay, so let me just zoom in. Not too much. There we go. Okay. So what are the degree and leading coefficient of the polynomial? So a polynomial is something just basically with variables. It has whole number exponents. There's no square roots with variables in them. There's no fractions with variables in the bottom, none of that kind of stuff. So it's, you know, a very plain looking algebra thing, basically. So this is a polynomial, and traditionally we write these so that your highest exponent is first, and then you count down with your exponents. So we would rewrite this. My highest exponent term is w to the 9. So I'd actually write this as w to the 9 first. Then I have this negative 23w to the 6. So that would be the next term. Now, the last two terms we have here don't have exponents, but you always write them with a w before you write any regular numbers. So that's going to be negative 9w, and then we have our minus 20. So this is what's called standard form, where you are writing it from the highest exponent down to the lowest exponent. And this is what allows you to determine the degree and the leading coefficient. So the degree of a polynomial is the highest exponent if there's one variable. If you have multiple variables, then you have to add the exponents together. But in a case where we have one variable here, it's just the highest exponent. So our degree would be 9. The leading coefficient is the number that's in front of that term. So we don't have a number in front of here. So if you don't see a number, you treat that as a 1. So our leading coefficient is 1 because there's no number in front of there. So the degree is the highest exponent, and then the leading coefficient is the number that's in front of that term. And this is terminology with polynomials. It's the degree part actually shows up quite a bit. That's pretty important. And that will come up later in the class when we start looking at polynomial functions. So if there's one thing to take away, the degree is important. The leading coefficient is important as well, but not as much as the degree. Here's another one. We want to give the degree of the polynomial, and this one has multiple variables. So this is where I said that if it's a one variable, you just take the highest number, but if you've got multiple variables, it's a little more complicated. So, and putting something in standard form here is more complicated as well. So I'm not going to bother with putting it into standard form because we don't really need to do that with the degree in a case like this. So we're going to look at each term, and I'm going to just kind of color code these terms. They are basically the things separated by pluses or minuses, but the minus always goes with the term. And then a plus is just kind of considered the separation. So we've got 4 terms here. So we've got a -3. We have a negative x to the 9v. Welcome, James. I am currently going through operations on polynomials, but I'm starting with the definitions involved with polynomials. So that way we have a firm kind of understanding of what you need to do, or at least understand what's going on here before you can get to the operations. So we've got 4 terms here, and any variable that doesn't have an exponent, you can write an exponent of 1 for it. So like that v doesn't have an exponent, so I can give it an exponent of 1. So when we're finding the degree of something like this, we're looking at the variables and their exponents, and you look at the degree of each individual term. So the degree of each term. So the -3, if it has no exponent, has no variable, that has a degree of 0 because there's no variable, so that we call that 0. My next term here, I have a -x to the 9th, v to the 1st. So what you do is you add the exponents on those variables. So this would be 9 plus 1, which is degree 10. The next term, we have a -2. That number doesn't matter. We're caring about the exponents. So we've got v to the 3rd, w squared, x to the 6th. So you add all of those exponents together, 3 plus 2 plus 6. So 3 plus 2 is 5, plus 6 is 11. So this is going to be 11. And then the last term, we have 6w to the 9th. So it's just the highest exponent when there's one variable, so that is 9. The degree of the polynomial is the highest out of all of these numbers. So because 11 is the highest number that we got out of all 4 terms, the degree of the polynomial is 11. So it's the highest out of all of those exponents, just like in the previous example that I did. It's just that involved one variable, so we didn't have to add exponents together to get the degree. Are there any questions? Okay. So operations. What kind of things do we do with polynomials? So we can add polynomials, we can subtract polynomials, we can multiply, and we can divide. But we are not going to be dividing polynomials this week, don't worry. So let's take a look at, I've lost my mouse, there's my mouse. Let's take a look. This is an addition problem. So if it says simplify, it just means you're going to be combining like terms. That's what that means. And when you have an addition problem with polynomials, that means you can just ignore all the parentheses. They're not necessary. They're only there to indicate we have 2 polynomials, but they're not needed because there's no numbers in front of them. So you can rewrite this whole thing as 5v squared minus 6v minus 7 plus v squared minus 4v plus 2. So because that plus and then there's no number in front, it's just the parentheses are irrelevant. So we're going to combine like terms, and if it helps, anywhere that you see a variable without a number in front, you can add a 1 so that you can see that those combine together. So we have a 5v squared and a 1v squared. Those are like terms because they both have v. They both have the same exponent. They both are exponent 2 on the v, so we can add those together. 5 plus 1. So it gives you 6v squared. Next, we have a -6v, and then we have a -4v. They both have v's. They both have no exponents on them, so those are like terms. And you just look at the numbers, and -6 minus 4 is a negative. So we get a -10v. And then you're left with the numbers. You just can combine the numbers. You have this -7 plus 2. Negative 7 plus 2 is negative 5. And then that is considered simplified because we've already added everything together that we need to and that we can. So that is simplified. Now, what if it was actually a subtraction problem instead? If it's subtraction, we have more steps to do. We can't just ignore the parentheses. People tend to do that, and that's where they mess up. So with a subtraction problem, you want to think of the subtraction as adding a negative 1 and then multiplying by whatever's in parentheses, because subtraction is the same as adding a negative. So the first set of parentheses we don't need because there's no number in front to multiply by. So I can leave those off, but I'm going to rewrite this as a negative 1 times the second set of parentheses. Subtraction is adding a negative. And then we're going to distribute through the parentheses. So everything through the parentheses has to be multiplied by that negative 1. So I have a negative 1 times a v squared. And then I have a negative 1 times a negative 4v. So the negative 1 times negative 4, that's a positive 4, and we have our v. And then I have my negative 1 times 2, which is negative. And then I can, everything else I didn't touch, so I can just rewrite that. So you can see that all of the signs changed when we're doing a subtraction. So you can see that the signs for the last three are the opposite of what they were in the first problem where it was addition. So subtraction basically changes those signs. And that makes our answer different when we start combining like terms, because we have a 5v squared, but now instead of adding, we're subtracting a 1v squared. So 5 minus 1 is a 4v squared. Then when we have our v, we have a negative 6v plus 4v. So negative 6 plus 4 is a negative 2. And then we have a negative 7 minus 2. Doesn't show up very well with the red, but negative 7 minus 2 is negative 9. So you get a totally different answer just by changing that addition to a subtraction. It changes your whole thing completely. Are there any questions on those? Now the third operation that we do is multiplication. So I'm going to use the same polynomial. Oops, I didn't mean to zoom in. I'm going to do the same polynomial and I'm going to be multiplying here. So what if we had 5v squared minus 6v minus 7 times v squared minus 4v plus 2. So we're doing a multiplication. So multiplication problems where you have 3 terms and 3 terms, I usually make what is called a table. So I've got 3 terms here, and then I'm multiplying it by another 3 terms. When you do the multiplication, you are going to have 9 terms. You're going to have 9 things written down that then you have to combine. And because there's 9 of them, it's hard to keep track. So I make a table, and I start with my first polynomial, and I have that going across the top, and I leave a gap because I'm going to be adding lines in between, and I'm going to need room for actually doing some multiplication. So I'm filling in a table there. And then going down on the left, I'm going to put the second polynomial. So we have v squared, negative 4v, and 2. So this gives me a grid, basically, and I have 9 boxes that I have to fill in. So I know that if I multiplied these and I didn't fill in all my boxes, that I made a mistake somewhere. So this helps you keep track and make sure that you've multiplied everything and you've multiplied what you're supposed to. So this works like a regular multiplication table with numbers where you are multiplying a row by a column. So we're basically taking this row and then I'm multiplying it by what's in the first column. So the box that has both is going to be a v squared times a 5v squared. So you're multiplying row by column where they intersect. That's what you're multiplying together. So v squared times a 5v squared. So it's basically a 1v squared times 5. So that's going to be a 5. And then when you're multiplying v squared times v squared, you add your exponents. So I'm going to just write this down. So that's going to give us a 2 plus 2. We're going to end up with a v to the 4th because you add your exponents there. And if it's helpful, anything that doesn't have an exponent on a variable, you can write a 1 there. And I can even put a 1 here if you want to remember that you have to multiply that 1 up. So I've multiplied that box. Now I'm going to take the second column. I'm still going to do the first row and I'm going to multiply it by the second column. So I'm still taking the 1v squared, but now I'm multiplying it by negative 6v. So 1 times negative 6 is negative 6. And then I add the exponent. So it's going to be 2 plus 1. And I'm going to just write that in. I can simplify it later. Now I'm going to take my last column to multiply it by that row. And I have a 1 times a negative 7. So we get a negative 7 and then a v squared. Now, if at this point, I always recommend doing your math in pencil so you can erase. So I can combine these exponents and I can make that a 5 to the 4. And then I can add the 2 plus 1 and make that a 3. So you can then simplify those. And I'm going to make this line much thicker here so it looks a little, oops, might be too thick. But I want to make sure it's really obvious where my table is because otherwise it might get confused. Okay, so once you have the first row, then you're going to take the second row and then you're going to repeat the same process. Second row, first column. So I have a negative 4 times 5, which is a negative 20. And then that's a v to the first. So that's 1 plus 2 on my exponent there. I add those exponents. The 2 comes from the v squared, the 1 from the v to the first. Then I'm going to move to the second column. And so I'm taking the negative 4v times the negative 6v to the first. So you want to make sure you're multiplying by the things that are above my thick lines. That's why I try to draw a thicker line so that it makes it clear what you're actually multiplying by. So I have a negative 4 times a negative 6, which is a positive 24. And then they both have exponents of 1, so I'd be adding 1 plus 1 together. Then the last column, I'm going to take that negative 4v and I multiply it by negative 7. So negative 4 times negative 7 is a positive 28. And then I just have that v. So now I can go back and and I can add my exponents. 1 plus, oops. This is the problem when I don't have perfect precision on my tablet. I'm erasing too much. But you add those exponents, you're going to end up with a v cubed from the 2 plus 1, and then a v squared from the 1 plus 1. And then you've got your last row that you're going to multiply by, and you're going to multiply by the first column. So we're doing 2 times 5v squared. Do 2 times 5, which is 10, and then v squared. The variables just kind of hang out. They don't go anywhere. Then second column, we're going to multiply 2 by negative 6v to the first. So 2 times negative 6 is negative 12, and then we just have a v. And then you're doing that last column times the 2. So it's 2 times negative 7, which is negative 14. So now I've multiplied everything. I filled in all of my boxes here, so I know I've multiplied everything that I needed. And now it's time to combine all of your like terms. Now, if you noticed, I'm going to highlight my like terms here. They tend to collect along the diagonals. So everything with a v squared is on a diagonal here. Everything with a v cubed is on a diagonal. And everything with the v is on a diagonal. So those collect along the diagonals. And so we can combine those together. So this is actually similar to what is called the lattice method of multiplying, which they do in Japan, actually. So basically, you're just kind of drawing lines. So we've got 5v to the fourth. And then through here, I'm going to add my like terms. Negative 20 minus 6. I get a negative 26v cubed. So I'm adding my yellow, which are like terms there. Then I go through my next like terms. I have 10 plus 24 minus 7. So 10 plus 24 is 34 minus 7. We get a 27. So this is going to be 27v squared. Then I have my green. Those are like terms with the v's. I have negative 12v plus 28. So that's 16v. And then I'm left with a negative 14. And then all of this forms my result. If I add all of these together, my answer is 5v to the fourth minus 26v cubed plus 27v squared plus 16v minus 14. And this method works if you have two things that you're multiplying in 2 terms instead of 3 terms. This works if you have 1 term times everything else. It doesn't matter how many terms you have, this method will work to do the multiplication. It doesn't matter which position these things are in, if you have 2 things times 3 things, none of that matters. The multiplication still works. You'll still get the right answer. Are there any questions? Very cool, yeah. Yeah, I don't think, I'm trying to remember if our book actually teaches this method of multiplying. Actually gonna open up the book. I usually don't use this if there's 2 things times 2 things, because then I'll just do FOIL. But if there's anything bigger than that, I'll use this method because it's a lot easier to keep track of. Yeah, it looks like our textbook does not do this method. Our textbook is showing it sort of like you do regular multiplication, and I think that's a lot harder. And so there's another example where they just use lots of arrows, and you can get lost with lots of arrows. So this is the method that I prefer, because then you don't have arrows all over the place. So that is, in essence, the section on operations on polynomials. So that was what Bonnie had said that she wanted to have some help on. James, is there anything in particular that you need some additional help on, either for week 2 or week 1? You're welcome to, if there's a topic you need some help on, you can type that into the chat box. If there's a different topic, Bonnie, if there's something else you want to see, you can type that in the chat box. I am open to do whatever you guys need examples on. Okay, no problem. You can chat if you don't want to turn your audio on. Audio is nice, it's quick, but chat box is fine too.
Okay, can you hear me?
Yes, I can.
All right. So I mainly just wanted to watch somebody else work through some problems, but I did have one question on factoring out a greatest common factor on one of the problems. I could type it into the chat if you want, because my main question is why they factored out a negative versus just using a positive greatest common factor.
Yes, that is an excellent question. Was this on the homework?
I think it was. I know it was in one of the videos.
Okay.
And I couldn't find any information on why the negative.
I'm going to open up the homework and see if I can see if the question, I'm pretty sure I would have assigned. I wrote the class, so, but I don't remember. I'm like, which questions did I pick? Because there's so many questions. Let me see.
I will type it in and see.
Yeah, you can type it in too. Oh yeah, that makes perfect sense.
Okay.
Yes. Okay. So we want to factor out the greatest common factor, and we have negative 12x to the 4th minus 6x cubed plus 9x squared. Okay, so before we do any factoring the greatest common factor, you always want to make sure it's in standard form. So you've got the highest exponent down to the lowest, which is what we've got here. Then, whenever you have a negative in front, you always factor out the negative. Always. And there's many reasons why we do this, and it's mainly to make things easier down the road. So when you get to where you're going to have rational expressions, which are fractions with these things on the top and the bottom, we want to cancel things out. And if you have a negative in one and not in the other, you can't cancel. But what often happens is you factor out that negative 1, and then that allows you to cancel things out. They start matching. Another reason is when we're solving. When you're solving something that's quadratic, which you're going to get to, is it next week that you're going to solve? It's either next week or the week after that. You're going to be solving quadratic equations. And when you solve, we like to solve with positive numbers in front, because it just makes it a lot easier to solve, and we can just divide a negative out, because you usually have one side equal to 0. You can divide a negative. You don't have to deal with any negatives. When you factor by grouping, oftentimes the only way that the factoring by grouping works is if you factor out the negative, because sometimes you'll have things that you can group, but if you don't factor out the negative, then they don't match and you can't go further. So the general rule is if that first term has a negative, just always factor it out because it will save you work down the road. So in a problem like this where all you're doing is factoring out the greatest common factor, it doesn't matter. But when you're doing things later on where you're going to have to do some solving or you have to do some simplifying and cancel things out, then it does matter and it makes things nice. So I always say, okay, my first term's negative. I'm going to have a GCF net that's negative. So I always start by identifying my GCF. I know I'm going to have that negative. And then I look for the numbers. So I'm going to just do the whole problem because it's good practice. So I'm looking for a number. Preferably you want the largest number that you can divide into 12, 6, and 9. So I can divide 6 into 12, but 6 does not go into 9 evenly. So then I have to look at the next number that divides into it, and that's 3. And yes, this is only if the first term is negative. So it doesn't matter if any of the others are negative. If that first one's a negative, I'm going to always take out a negative GCF. So I'm going to take out a negative 3 here because the beginning term is negative. Now I'm going to look at my variables. I've got x to the 4th, x cubed, and x squared. So if you've got a variable in every term, then you can factor it out, and you factor out the smallest exponent. So the smallest exponent here is x squared, so I can factor out an x squared. So that's my greatest common factor. It's going to be negative 3x squared. So the book, how does the book show the work? Because I generally show my work differently than the book does for factoring. Yes. So I'm going to show you guys an alternate way to show your work for factoring out the greatest common factor. And this way may make sense to you, it may not. I find this way helpful. I never used to show it this way until I got to calculus, and I found that I needed to do it this way, and I thought, oh, then maybe I should start teaching it this way because sometimes we got people that have to go to calculus. So my method for showing your work for factoring out the greatest common factor is I set it up so I've got my greatest common factor in front, and then I have in parentheses, and then I take each term of my polynomial and write it over the greatest common factor. And you just do that with however many terms that you have. So you're just going to take each term and create a fraction with it. So I put my greatest common factor in front, and then I'm going to have negative 12x to the 4th over negative 3x squared plus, and then I'm going to put the negative again on top, negative x cubed over negative 3x squared, then plus 9x squared over negative 3x squared. So it looks messy, but I do this, one, because calculus has to write something like this sometimes to solve problems. 2, it actually makes it easier for you to see what you're dividing and to get your signs correct, because that's one of the most common errors, is messing up a negative sign somewhere. And then it also makes it easier for you to see what cancels out so that you get a result of 1. Because a lot of people will divide things out and then they forget to keep a term there and they just ignore it and they somehow lose terms. So I rewrite it this way, and then I keep my GCF in front, and then I simplify each of these fractions following our rules of exponents. So with the numbers you just divide, so negative 12 divided by negative 3 is a positive 4, and then you subtract the exponents, top to bottom. So 4 minus 2 is 2, so that's going to be x squared. Then I have a negative 6 divided by negative 3, so that's a positive 2. And then you subtract the exponents. 3 minus 2 is 1, so that gives me an x. And then I have a 9 divided by a -3, so that's going to be a -3. And then when you subtract the exponents, you get 0. So that means the x doesn't show up at all, and it would just be times 1. So I just am left with that -3. And it makes it kind of clearer. You can see that those basically just cancel out there. So this is how I show my greatest common factor, which is different from what the book does. But this, I think, I don't know, I just like it better ever since I discovered that this is a method that works. I think it just makes it a little clearer, and as long as you know your rules of exponents, it's just, you don't have to do too much thinking to try to split things up in a way to make it work. You don't even have to really think it through. You just kind of follow the rules. Do your division, subtract your exponents. Yeah, exactly. It shows what's happening in your head anyway, and I think it's easier to check your work this way, because if you skip the step or you're trying to do it on your own and you mess up, it's harder to find where you might have messed up. But at least here you can see the steps, and you can kind of double check, did I divide that correctly? Did I get my exponents right? You know, that sort of thing. Generally then with factoring, if you get something that's x squared, you would try to go factor further. This does not factor further, but if it did, it's a lot easier to factor something with an x squared when it's a positive number, positive coefficient, than if it was like a -4 in front. So that's also why we take out the -3. Does that help?
Yes, that's actually exactly what I needed to know.
Good.
I can follow the rules. I just like to know why I'm doing it sometimes.
Yeah. So. It's hard because for some people, they want to know the why, but they're not at the point where it makes sense yet. Or sometimes the why is so far down the road that it's just like, just trust me, it'll make more sense later on. But something like this, it's like, okay, we're close enough where you can see where it makes sense, and it's not going to confuse you too much. There's some things where I'm like, just don't worry about it, just learn the rules. You'll figure it out later.
Yep, I appreciate that. Thank you.
You're welcome. We haven't had anybody else to join. Bonnie, have you thought of any questions or anything? Or James, if you have more questions, I'm going to be sitting on here till 8, but if you guys don't have any more questions, you don't have to sit here the whole time, but I'll be sitting here.
Yeah, I don't have anything else right now, but I'll probably just hang out a little bit and see if I can watch somebody else just in case.
Just in case someone joins.
Yeah, and it might ring a bell for me too, so.
Okay.